In this problem, we're going to expand a little bit on the quarter car model that we looked at in a previous example. The main difference here is that we are going to account for the mass of the tire or the wheel itself in this model, where it was ignored in the previous one. And we're going to be looking for the transfer function for the chassis located at y and its displacement relative to the input displacement u at the ground. And we're going to find a second transfer function for mass 1, which is meant to represent the tire, at x. So we want to find two transfer functions here, x over u and also y over u. Mechanical system, we'll start with our free body diagrams as we've done in the past. So first free body diagram, I'll work from the top to the bottom here. Well, let's look at our system first. We have a mass m1 and a mass m2. So each of those are going to need their own free body diagram. And there's no nodes here that we want to model because k1 is attached to m1, which then in turn is attached to k2 and b. And P we do not want to model because we have that input displacement U. So like the previous time we did this, we don't model that. That U will come into play in a force, but U is not a force, it is a displacement. So my first free body diagram, let's see what M2 is doing. I will use the given degrees of freedom here. So Y is defined as positive up. So on M2, it's attached to K2 and B. So the spring force, K2, is going to be, now we can use our method for determining the sense of the 2 degrees of freedom it's attached to. So Y at the top, X at the bottom. So let me start with Y, let's say. So let's hold X steady. Does a positive or a negative Y put K2 into tension? In this case, if Y is positive, that will stretch K2. So this will be a positive Y. The way the X is facing in this one, a negative X, so if M1 goes down and we hold Y steady, or the top of K2 still, a negative X, M1 going down, will stretch K2. So negative X causes tension. Now, because they're in parallel here, the same idea is going to be true for B. A positive y velocity will cause B to go into tension, and a negative x velocity will cause it to go into tension. And M2 has inertia to it. It will go in the direction of the positive sense of the axis, or of the degree of freedom. So M2 y double dot is the inertia. And then I will have here my picture 2. This will be M1. Forces acting on M1. Well, first, its degree of freedom. I'll use, again, the provided one, that x is positive up. I have K2 and B. Well, most of the work is already done. I assumed tension in the first picture. I will also assume tension in the other side of the picture. And those quantities, those values, remain the same because I assumed tension everywhere. So that part's easy. Now, though, I have the tension in K1. At the bottom, it's connected to P with a degree of freedom U. So the bottom can move, as can the top. So again, I need the net displacement here of this spring. If I were to hold U at 0, so it's just flat, a positive X stretches K1. And if I hold X at 0, a negative U as it's defined, so that point going lower than that point, negative U, causes it to go into tension. And those are the only 3 forces acting on M1, and I have its inertia, M1 x double dot. All right, so if you go and look at the previous time we did this, it looks pretty similar. Some of the degrees of freedom are different, and this M1 was a node and not a mass before, but largely it's going to look similar to the simpler version of this quarter car model. Using these free body diagrams, I will get 2 equations of motion. So the first one, I will look at picture 1 and some forces in the y direction here. Now, these are point masses. We don't have to worry about their rotations. They cannot translate left-right. They can only translate up and down. So I only have to worry in picture 1 about summing forces in that vertical direction. So y is positive up is my axis. So I'll have going down a negative k2 y minus x and a minus b y dot minus x dot. They're both negative because their arrows point down and y is defined as positive up. Equals, now I have this arrow is in the positive direction, so a positive m2 y double dot. I will work on the algebra on that one in a bit. I will get my second equation of motion though while I'm here, and that will be using picture 2 in the x direction. So now, for this picture, the arrows are up on k2 and b. So positive k2 y minus x plus b y dot minus x dot. And then minus, the k1 arrow goes down in the negative x direction, k1 x minus u, and then the right-hand side is an m1 x double dot. Now I'll work on these equations of motion a little bit. I'll start with 1 and go to 1a. Here I will distribute my parameters. So negative k2y plus k2x minus by dot plus bx dot equals m2y double dot. And I will also do that for 2a. I'll keep 1b below 1a here. So distributing this k2y minus k2x plus by dot minus bx dot minus a k1x plus k1u equals m1 x double dot. Going back up to 1a, this is where I will do a Laplace transform to get from the time domain into the frequency domain. I have a negative k2y plus k2 capital X minus a bsy plus a bsx equals m2s squared times y. Once again, when I'm doing the Laplace transforms of the x dot, the y dot, and the y double dot here, we are told that the system begins at equilibrium. So all of those initial conditions are 0, and that's why we get the simplified sy, sx, or s squared y. And the same will be true from 2a to 2b. All right, I will do the Laplace transform of 2a here, and we'll see when we count up our outputs that we have these necessary steps. So k2 capital Y minus k2 capital X plus bsy minus bsx minus k1 big X plus k1 big U. U is our input, so it is a function of time, so little u goes to big U, equals m1s squared capital X. All right, now let's look at what we have so far. Outputs between 1b and 2b. So these are the dependent variables that are not prescribed. They're not inputs, obviously inputs into the system. We have x and we have y. And input, 1b doesn't have any input, but 2b does. We have u. We have two equations, 1b and 2b, in the frequency domain, and two outputs, x and y. So this will be solvable. I will be able to get what we're looking for. In this example, both transfer functions, x is an output and y. Because we have two equations for these two outputs, I am going to use Mathematica to simplify the algebraic work that we're going to have to do. In Mathematica, I will put in my two equations of motion. So equation of motion 1, I have a negative k2y plus k2x minus bsy plus bsx double equals m2 s squared y. Right, so that is 1b translated into Mathematica. Now I'll put in 2b. So equation motion 2 is k2y minus k2x plus bsy minus bsx minus k1x plus k1 big U equals m2 m1 s squared x. And both of those we just want to check, and those are the two equations of motion that we came up with. Now we can go and start to get our two transfer functions. So I want to solve my two equations of motion simultaneously for my two outputs, x, y. All right, and Mathematica did the algebra for us. We have a decent number of terms here, so this would have been a little bit of a hassle to do by hand. I'll simplify this to just the one. All right, so we have x, and then on the right-hand side, we have this expression. We have a u on top. That's our input, so that's okay. And it's nothing's in standard form yet, but we'll get there. And then y, we have its transfer function as well. So I'm going to clean this up and get my tfx. So this is my transfer function for x. This is my x over f. So I'll take that and paste it in here. Remember, it's x over u, so this effectively divides out the u. Now, it's not quite in the form that I want, so I will redefine it here with the collect. So let's collect tfx. And we want just the numerator first, so we do have to specify that. So the numerator and the same thing for the denominator. All right, so it took that above expression and now it's putting it, well, closer to the final form that we want. I'm grouping the coefficients in front of powers of s. Now it is ascending right now, but we'll rewrite it in descending order, which is the standard form we want to express it in at the end. Now I'll do the same thing, the same basic premise for my transfer function for y over my input u. So I'll define tfy as, and now I'll copy the y expression and paste it. The denominator is exactly the same, but the numerator is different. It's y over u, so I divide through by u and define tfy. And now I just want to express it in this better form where it's going to collect my variables for me. So I'll just paste that and change this to y and change this to y as well. All right, so now it's in that better form for the next step. It's going to make it easier to write out because I've collected my coefficients. I've copied out the Mathematica output so that I can handwrite in the standard form my two transfer functions. So I have my x over u is going to be the top one that I copied out. Remember, I want descending powers of s. So I do have to reverse this, k1 m2 s squared plus bk1 s plus k1 k2 over m1 m2. This is now a fourth power in the denominator, or degree 4, plus bm1 plus bm2 s cubed. If you look back to the simpler version of this, where it was a node instead of a mass at the wheel, that was only third order. Plus, I have k2m1 plus k1m2 plus k2m2 s squared plus bk1s plus k1k2. So, somewhat long expression here. Again, this is only 2 degrees of freedom, 2 masses. And I have y over u. So the numerator is the only thing different. in descending order now, b k1s plus k1 k2 over that same denominator, m1 m2 s to the fourth plus bm1 plus bm2 s cubed. And I have a k2m1 plus k1m2 plus k2m2 s squared b k1s plus k1 k2. So this is what I was asked to find were the two transfer functions for two outputs, the x position of the chassis and y the position of the tire or of the wheel. So in the previous examples, kind of as a byproduct of using Mathematica and solving for all of the outputs, we were always generating really all of the transfer functions, but we were typically only interested in finding one of them and putting it into the standard form. In this example, though, we did want both. As a recap, to get to these transfer functions, we started with our given diagram. We had to draw the two free body diagrams, one for M2, one for M1. We need one free body diagram per element in our system. Here we had two masses. We did not draw a free body diagram at P because we don't want to draw nodes where we have a prescribed displacement like we did as our input in this system. So two free body diagrams. We summed forces vertically in the first one and in the second one to get two equations of motion. I manipulated some algebra, did some distribution to write 1a and 2a from just expanding 1 and 2. Then I went from 1a to 1b with a Laplace transform and 2a to 2b with a Laplace transform. So 1b, 2b are the two equations of motion now in the frequency domain. Counted up from there, my outputs and my input. I have one input u that was given to us and two outputs x and y, those two displacements. So between my two equations, 1b and 2b, and my two outputs, I have a solvable system for finding my two transfer functions, x over u and y over u. I let Mathematica do the algebra for us instead of trying to do it by hand, so I solved 1b and 2b for x and y. Did some manipulation, and I was able to get then these two transfer functions, x over u and y over u.